In this video, I will describe a pipeline I've set up which will load various different targets with the latest firmware. I will do a simple demo where I will change the frequency of the LED blink, then I will describe the hardware setup, and finally I will walk through the steps of the pipeline. Notice the LEDs are blinking at 1 Hz. Now I will modify the application to blink at 10 Hz. This is the blocking delay, which I will change to 100. I will commit this change and push it up to master. Origin. Now, the frequency will slowly start changing one by one. The hardware setup is as follows. A SAMD 20 explained kit, SAMD 21 explained kit. This is a custom breakout board for a SAMD 10. All these are Cortex-M0 parts. This is debugged with a USB debugger with the EDBG chip inside. This is an Atmel-ICE. These two boards have the same debugger chip on board. This is a STM32 discovery kit, also with a ST-Link debugger on board. This is a Arduino Duo flashed with the Atmel-ICE. Arduino Duo is a Cortex-M3. The STM part is a Cortex-M4. At this point, all of the LEDs have changed. All of these parts are debugged via USB. You can see all of the USB connections going to this hub, these two hubs. The USB host is a Beaglebone. The Beaglebone is controlled via Ethernet, going to this switch, and out to the internet via this laptop, which is bridging the Wi-Fi in this house to the LAN. The idea is that this laboratory could be located remotely from the development stations. The pipeline consists of the following steps. The source code is modified, a git push triggers a webhook to a Jenkins server, which will build the firmware for all the different targets. The built images are published to a web server. In addition, there is a mapping on this web server which maps each target over there to the appropriate image which should be loaded onto that target. After this happens, the Beaglebone is polling the web server and we'll see that there are new images to be loaded onto the different targets. The Beaglebone will then handle everything from there. Now I will describe the polling loop on the Beaglebone. Here I have SSH'd into the Beaglebone. There is a script loop which simply loops and individually polls for each of the targets. Let's look at one of them. It starts here. A curl is done to the publishing server, and this URL is the mapping of the image to the development board. Doing this curl will return a file name of the semantically versioned ELF file, which is to be downloaded from the artifact server and loaded onto the target. If the image is already on disk, then nothing happens, but if the image is not, then it will be fetched and flashed to the target. This is done using OpenOCD. For example, I can do this curl individually, and you can see it returns the name of the ELF. The application works as follows. This app.c is compiled and linked for all the different targets. FreeRTOS is already portable and ported to all the different targets. In addition, I have created a portable hardware layer. Here it is initialized, and in the FreeRTOS task, the LED is simply toggled. The structure is here. Under the port directory, we see all the different ports. For example, this is the STM port. The hardware port is here, and we can see there is STM specific code in here to initialize and set the LEDs. Now, if we look at, say, the Arduino Due, we can see there is Atmel specific code here. Notice these function names are the same. All of the images are built using CMake. The top level CMake simply specifies each port as a subdirectory and is built accordingly. This is the CMake build, and the outputs will appear here. As you can see, they are tagged with version number and commit SHA. The port for each target will specify other information such as linker script, the startup code, vector table, compiler flags to set the architecture. In addition, the clock speed is set as a compiler define, which tells FreeRTOS how many ticks are in a millisecond. The Jenkins job is specified using job DSL. Here we see the webhook trigger, and it simply runs the build script and publishes the ELF files to a web server, which happens to be located on the same. Then the paths to all of the generated images for each of the targets is recorded here. Finally, the mapping is made, which maps the target to the programmer that the target is attached to. You can see here I have multiple Atmel-ICE debuggers. In addition, one Atmel-ICE debugger is connected to a SAM-D10, whereas the other one is connected to a SAM-3. To support this, the serial number of the debugger is specified. On that same note, notice here I am logged into the Beaglebone. These are the polling scripts that the Beaglebone will poll the server with. Notice at the top, these two are almost identical except the target microcontroller is specified at the end. This is because Atmel-ICE can flash either one of these targets, but the target has to be specified when driving the programmer. So at this point, the loop individually polls all of these. However, the serial number 5898 here is polling for SAM3X, which is the Arduino Due. If I were to disconnect the programmer from the Arduino and connect it to, say, a SAMD20, then I would specify here that the programmer is connected to the appropriate target. One more note about these two polling scripts. Really, the difference between them is simply specifying where the OpenOCD config file is. You can see here there is a OpenOCD config for this serial number as well as the target. Here you can see all of the OpenOCD configs. The serial number as well as the target is specified here. To conclude, I will try to demonstrate all of the steps in action. Here I will start the polling loop on the Beaglebone. Notice nothing is happening because the targets are already loaded with the latest firmware. Notice they are still blinking at 100 milliseconds. I will change the application to blink back at 1 Hertz. I will add and commit. Now I will do the push and we will see that Jenkins will be triggered, and then very shortly after the Beaglebone will pick up the latest images. Finally, we will start to see the frequencies change. So here on Jenkins we see the trigger has happened. And a bunch of output is on the polling loop. Let's look at the Jenkins output, which is finished already. The images are being built, and that mapping is being done here. The mapping of the image names to the targets. On the Beaglebone, there is a bunch of OpenOCD output. And we can see here the frequencies are back to 1 Hertz. Thank you.